All right, how's it going? Questions? I'm doing well, thanks. The questions? Yeah.
I was having trouble coming up with how to best go about, like I know how to dump all the information from the file into my tree.
Okay.
To fill up my tree. But then to kind of like go through the game and do the whole yes-no thing with...
to play the game, basically?
Yeah.
Oh, okay.
I didn't know how to say that.
All right, so make a temp pointer, starts at the root. And while that's a question, print question. Get a yes/no answer from the user. And then set temp equal to the left or right subtree based on their response. Go back up. And if it's a question, print out the question, get a yes, no, move to the left or the right, and just keep looping as long as it's a question. When you exit that loop, temp is an answer. Print out the answer. So that's basically the complete gameplay from start to finish. And the overall behavior or program is the following. So step 1, read the tree from a file. Step 2, play game. Step 3, if you ended up guessing wrong, fix tree and write to file. And then step 4, go back and play the game again. So all of this is basically step 2. So you got step 1 working, you said, right? And that's probably the trickiest part of the whole thing, is the ingest from the file. Playing the game is really just kind of a traversal of the tree from root to a leaf, but you're going left or right based on whether the user says yes or no to each of the questions you ask. And the gameplay effectively ends when you get to a leaf node, right, which is no longer a question, so it's a node with no children. At which point you've decided what the person was thinking of, you tell them what you believe they were thinking of, right? And they tell you if you're correct or incorrect. If you're correct, just go back to number 2. If it's incorrect, then you've got to get the correct answer, get a discriminating question, update the tree, write it to file. These first 2 parts get you bunches of points though. Right, if you can ingest from the file and you can play the game from start to finish, that's, you know, more than half the challenge. And then the other piece of it is, you know, adjusting the tree and writing to file. So that's worth some number of points.
I have a question. So it might say in the assignment, I'll have to look, but do you want us to have it continually play the game over and over again? Okay.
Yeah.
I'll need to fix that.
Yeah, just throw it in a big loop until the user says, like, I don't want to play anymore or something.
Says I give up.
Yeah, yeah.
It's similar to discovery. So we're not guessing every single time. We only guess once at the end.
You're asking questions and getting a yes/no from the user all the way until you get to a leaf node. And at the leaf node, what's in the tree is an answer, so that's your guess. So now you say, okay, you're thinking of a rock, right? And then they say correct or incorrect, yes or no.
And then, what do we do if it's incorrect?
That's a whole nother story.
Yeah, we have the, like.
So, my guess. So you make your guess. Let's say it's in a variable called my guess. Okay, so that's the data of the leaf node. And you say, is that correct? And the user says no. Okay, so ask the user for the correct answer, which was something like a duck. And then ask the user for a new question, which might be, does it quack? Right, you have to tell them what kind of question to provide you with. So it could be a question where yes means duck and no means a rock. Okay, so the question is, does it quack? So now you build yourself a tree containing 3 nodes. The root is the new question. Does it quack? The yes answer is the correct answer. And the no is the incorrect answer, which was your guess. So you make that 3-node tree, and as you were traversing, and you got down to a point where you decided, okay, it's a rock, right? And that was not the correct answer. You change this node from being a leaf node to being the root of this little subtree you just created. So now if you got to the point where you would have said it's a rock, instead of saying that, you go ahead and you ask the new question, and then you conclude either that it's a rock or whatever the correct answer was. Does that make sense?
Question. Does it matter like how we're expecting the user to format?
No.
Okay.
So long as you clarify, you can say, give me a question for which yes is a rock and no is a duck. Or you can say for which yes is a duck and no is a rock. I'm not specifying that, right? As long as it's clear to the user how they should form the question, right? And then you put things on the correct side accordingly.
Well, maybe more of this thing is, it might look weird if like my file is like a turtle in like the actual file.
Oh, no, don't worry about it.
Yeah.
There's too many parameters. It's like putting question marks on the end. Sometimes you get double question marks and so on. That's okay. So other questions? We can go on to PA5. Yeah.
I don't know if this is too personal for my code.
Okay.
But with the node left right traversal, and you're writing to the file, and it's the recursive thing. I'm trying to figure out a way, because when you're doing recursively, it's always skipping a line. So at the very end of my file, I have a blank line, and I can't figure out how to get rid of that.
Doesn't do any harm, does it?
I guess I haven't tried. I figured it would do harm because, like, you check to see if there's another line before scanning the next thing.
If you're doing the ingest correctly, it should always read the last leaf node, and it should stop trying to read at that point. It should never actually try to read past the end of the data.
Because if you're printing an empty line, wouldn't it keep printing an empty? Like it would just keep appending another empty line the more you play it.
You're only printing from the tree. So if writing your tree adds an empty line to the end of the file, your file will always have one empty line at the end. That's okay. But how do we do this
I guess I could
pre-order?
try without.
Yeah, give it a shot.
Ask the player, is it a?
Yeah.
How do you know?
So how do we write the tree? So we want to do node left right. set your temp to the root. Well, right tree. Let's just write a right tree method. If you pass the root of the tree you want to dump out to the file, right? So, so if it's an answer,
Yep, I guess it's fine with that extra line.
is it? Okay, good.
I don't know why I assumed it wouldn't be.
So if you had an answer point in your tree, right, if there's no children, just write out an A followed by the data and return. Otherwise, write out the root node as a question. Okay, so that writes the node part. And now you want to recursively write the left subtree. So if root.left is not null, right tree root.left. And then if the right tree is not null, write the right tree, return. So it's kind of like traversing a tree, right? Deal with the node itself, which in this case we write out as either a Q or an A, depending on whether it's a question or an answer, and then use the right tree routine on the left subtree and the right subtree recursively. That does the L and R parts. Yeah.
So we know the root's not now, right? Because we're always going to start with.
The first time through, but when you call right tree root.left, right, it could be null.
But, you don't
But
have
yes,
to
you can
check.
assume that there's always a tree there.
Right, so you don't have to check before doing the.
So you don't have to check before you call right tree,
Yeah.
right? But you could put a check in here to say if the root's null, return, and then you don't need to deal with these things.
Right.
You just right tree left and right tree right. Yeah.
Does it try etch the root node
Oh, don't do that.
section?
Yeah, it could, but you really don't want to go down that path. That's the path of sadness. Yeah, you could. I don't know what that would do on Stack Overflow. That would be fun. Hey, I found an easier way to write this. Does this look good? That would be cool. I might do that.
Well, let us know what you get.
Yeah. You'll see the flames from wherever you are. Yeah, so that would work, right? Technically, you could just traverse down until you get an exception. But try catches are kind of a pretty heavy powered mechanism. They're kind of, there's no good reason why you shouldn't do that. But yeah, it would be an unusual style. But yes.
I was just passing I was kind of just doing one line, saving that as a string, and then doing the second line, which should have text on it, and then passing those into my right to tree.
Say that again?
So I was looking at the way the file should be formatted, and it should have like Q or A,
Mhm.
and then the next line should be the content for that,
Right.
that bit.
Mm-hmm.
And so I was just saying next line equals this string, and then another next line equals this string, and then keeping track of what those are.
Yeah,
And
yeah.
then instead of saying like if it's A, then because either way you need to save A or Q to the,
Mm-hmm. Right.
the node. So I didn't know if that mattered or not,
If I understand you, I think that's okay.
as long as I'm skipping the correct line.
Yeah.
That's what I was trying to do. I haven't quite gotten it to test
Okay.
it yet. So.
But you do need to look at the Q or the A to know whether, right, when you're ingesting, you need to look at the Q or the A to know whether to return at that point or to recursively call your ingest.
Oh, yeah, okay, because
Because if it's an answer, you don't want to,
keep
right,
going
you
down
don't want to
that.
keep going down through
Oh,
the file,
okay.
yeah.
That makes sense.
You got me wondering if you could write code without any if statements anywhere. Just by like translating each potential if statement into an exception or no exception operation and doing everything with try catch.
Wouldn't that stop your program then?
Not if you're catching it.
You can put a try catch in a while loop too.
Yeah,
right?
yeah. That's intriguing. I wonder what you'd get to there. Hmm. Yeah.
It's the program that's unbreakable.
Yeah, because it's broken. That's interesting. Okay, that's gonna be a late night activity. All right, other questions? So my suggestion remains, right, this is your basic PA4, right? So get that working first. And if you don't have that working, right, get this working. Build a tree just by cobbling together nodes and play your game with it, right? So that you can start with the first question at the root, move down to the left or right, keep asking appropriate questions till you get to an answer and say, okay, you're thinking of such and such. Forget about this part, right? Just play the game. And once you've got it playing a game with a tree in memory, then add your ingest function. The ingest is potentially tricky. If you set it up just right, it's really easy. But if it's not quite right, it can be kind of confusing to debug. So get that working. And once that's going, right, go after the big 20Q file in /temp. Read that in, play the game, and it should let you do a full, bunch of questions. Takes you down to duck, build, platypus, or whatever, right? And that tells you that this part's totally working. It tells you that the ingest is totally working. And now you can set all that aside and just concentrate on how you adjust the tree and doing this, doing the node left, right, traversal to write it back into the file. All right, any other questions? All right, so let's talk about client-server models of processing. This is a general model that goes back decades and it's still in use, and we use it all the time, even if we don't think of it while we're doing it. Every time you connect to linuxengrcs.com, you're engaging in a client-server style interaction. Every time you access a web page, you're using a client-server model. So this is a general paradigm. And it's built with two sides, right? Not surprisingly, referred to as the client and the server. So what is a server? Think of some agent that's hanging out waiting to do your bidding for you. Okay, so somewhere on the net there's a server called linux.engrcs.com, and it's referred to by what we call port number 22. And what this server is doing is it's waiting for someone to come along and say, hey, I'd like to log into this machine. And when you make that request, it will exchange some information with you so that it can do secure communication, it can do encryption, and then it will receive a username from you, and it will receive a password from you, and it will check to see if that password works for that username, and if it does, it will begin reading commands from you and executing them in a bash shell. And if it doesn't recognize your password, it'll say login incorrect, and it'll go back to the beginning. And if you get your password wrong 3 times, it'll say goodbye and disconnect. Okay? So the server is this thing sitting out there, typically on the web, but somewhere that's just waiting for client requests. Okay, and classic example of a server is the login server, which is something called SSHD. So it's a program that understands SSH communications. So let's hop into the Linux server. I probably don't have a network connection because I've been messing up with my computer. So there's a process out here, user sbin SSHD, it's process 803. That's the secure shell server, basically. And when you make a PuTTY connection to Linux and grcs.com, you're talking to this program. Okay, so that's the server, and your PuTTY program, that's what we call a client. And if you successfully negotiate a connection, then this process creates a new process. So in this case, this process right here, which is a copy of SSHD but dedicated to talking to Nick. And it actually creates a pair of these processes. So 803 is the server itself that created process 9090, which was used for talking to me, and 9090 creates another process, 9093, which is also used for talking to me. So we get two processes. Same thing when you access a web page. So I don't know if I can find it. Yeah, no. I don't know what the server is called. But there's a process that's waiting for connections from browsers that want to access web pages. Yeah, so it's Apache. So one of these, all right, so those are web servers. So 846 is the main one, and it creates children. All right, so how does this work? Well, you remember pipes from 224, right? You can run a command and it's generating output to standard out. You can have another command, it's reading from standard in. We can pipe these two commands together, so command 1 pipe command 2, and it basically creates this conduit between the two processes. And whatever this writes to standard out is now available when this reads from standard in. Right, do you remember this? Okay, so same thing happens with this client-server model. We have this pipeline, and the client can write into this end of the pipe, and the server can read from it. But it's actually a two-way pipeline. The server can also write into here, and the client can read. So you can send information back and forth. So these endpoints, these are called sockets. So to have two of these programs talk to each other, each one has to create a socket, and these sockets have to be connected together somehow. And I can, from this socket, create a scanner. So I can say has next, next, has next line, and so on, and read whatever's coming out of this socket, which is whatever this program put into the socket. And I can also create a print writer associated with the socket, so I can say print writer object name dot print line, and that will push things into this socket, and they'll be available to read from the other side of the socket. So you can take two programs, pass information back and forth through this conduit. Okay, the advantage over a pipe is these don't have to be running on the same machine. They can be anywhere on a network as long as they're on the same network. So if they're both on the internet, they can be anywhere in the world or on the space station or anywhere else that's networked in, and they can share information. And it's really no more difficult than talking over a pipe. But you get this ability to go outside of your local machine kind of for free. Or I can say I want the socket to be on the same machine as this, and it's kind of like a pipe.
Cram a file through that?
Sure. You can put anything you want.
Yesterday I was watching a YouTube video on how to take the tic-tac-toe game and then make it to where it goes over to the server so
Cool.
you can play with someone else. And so I was learning about sockets.
Okay, nice,
So it's
nice.
kind of cool. That was yesterday, and now we're learning.
Awesome. Cool. So yeah, any time that you have a program doing something, right, you can take one piece of this process and put it somewhere else, connect it through a socket. And this is a really useful model in general. So if you're communicating across the network, you need some way to identify this socket. And so we do that with two pieces. One is the IP address. What does IP stand for? Anybody know? Internet Protocol. Cool, everybody knows. So that's an IP address. Old school, it's 4 numbers, IPv4. Newer version, IPv6, so 6 numbers. Problem with 4 numbers, these are each bytes, 32 bits, that's 4 billion addresses. We are out of addresses. There's more than 4 billion things on the network. Right, so we had to switch to IPv6. Vince Cerf, who, one of the people who was working on this stuff in the early days, he claims it's his fault that we ran out of IP addresses, because his telling of it, I heard him give a talk at Tech, it was cool. His telling of it was, they had a big debate about should they use, 4 bytes or should they use more, because this might get really big, And his argument was, let's use 4, and if it works, we'll come back later and expand it. And of course, they never went back later and expanded it because that would be a lot of work, right? So we were stuck with 4 until we ran out, and we had no choice but to go back and do IPv6. So there's an address, right, which identifies usually a particular machine or system somewhere on the net. Could be a computer, could be a smartwatch, could be a cell phone, could be a refrigerator, okay? And then within that machine, there's a series of ports. So a port is just a single integer, 16 bits, and it lets you specify a particular one of these sockets on that machine. So IP address gets you to the machine, port gets you to a socket on that machine. And the combination gets you to a unique, typically server, somewhere in the universe. So there's conventions for what port numbers go to what. So for example, port 7 was reserved as an echo port, and if you connected to port 7 and you sent something to that socket, it would echo it back to you. So it's basic test.
Is that usually open?
No, so most of these are not open anymore. So back in the 70s, 80s, right, we weren't really worried about viruses, we weren't worried about denial of service attacks, so everything was open. And you could pick any machine you wanted, and you could send a message, you could establish a connection to port 7, send something out, and get an echo back, right? And the whole network used to be split into 2 main nets, 10 dot something and 26 dot something. 10 dot something was called ARPANET, 26 was called MILNET. And one was academic, one was military. So if you went to a random machine with a 26 address and started doing this, you'd get people upset. I got a friend in trouble once because she was working for the government, and I started poking around her machine, and she got called in by security and said, someone's like doing something. Do you know this person? Why are they doing this? So that was fun. So 21 was the old file transfer protocol. So you could establish a connection to a socket at port 21, and then you could say, here's my username, here's my password. It would authenticate you, and then you could say, put this file here or get this file from there. and it would start receiving or sending contents of files, and you could pull files between your machine and a remote machine. This was pre-encryption, so everything was done in plain text. So your password went across character by character in ASCII. And when you had wires running from your computer to another computer, that was fairly secure. When you started going wirelessly, that was completely insecure. And in fact, even plugging into a router, it's still insecure because somebody else plugging into that router can listen to traffic, right? So we don't use most of these anymore. But 21 was file transfer. 23 was a program called Telnet. That was how you created an interactive session. So you'd send a username, you'd send a password, it would authenticate, and then you could send commands, and it would go ahead and execute them as shell commands, take the results, send it back to you. So 23 we don't use anymore. We use 22, which is the secure shell daemon, SSH, and that puts a layer of encryption. So you don't send plain text anymore, you send encrypted. So 23 was Telnet. 25, simple mail transfer protocol. So you could talk to port 25 on a machine. You could say mail from, tell it who it's coming from, recipient to, tell it who to send it to, and subject and then body, type in the body of your message, and it would create an email message and drop it in this person's inbox, right? With no authentication of any kind. So you could send mail from the president of the company saying, you know, give all your money to Nick, and it would look like it came from the president of the company, right? And there was no way to tell any different because it was just reading from this socket. So we don't do most of these things anymore. But all of these ports were used for different things. There was a talk port. So 80 was the web browser. So you put in a connection to port 80 and you say, give me this web page, and it'll find the web page and send it to you with a bunch of HTML tags in it. And your client, your web browser, turns it into a page you can see. 79 was a finger daemon, so if you type finger on the Linux server, it shows you who's logged in, where they are, how long they've been idle, and so on. Well, you can get that information on remote machines by just talking to port 79. So this is a generally useful methodology, and there's tons of services, many of which are defunct at this point. But things like IRC, right, chat services, games that you can play on a machine and connect to other machines, all of those things are done through the same kind of client-server setup. So it's a generally useful model.
What port is remote desktop, or is that not a protocol? RDP?
It probably is, but I don't know which one. And I think these are mainly the ones that were sort of established a long time ago. So I don't know if it'll show up in here. But if you use something to run a remote desktop, you're basically going through a socket and talking to a server. So if you do netstat, that'll show you what's going on in your system right now network-wise. And I just put it into grep for TCP. So these are all the TCP-related activities. TCP is like IP, Transmission Control Protocol. It's a layer that sits on top of IP, and it basically means we're doing sockets with this client-server setup. So there's a number of things that are in this state called listen. It means they're waiting for connection requests. So there's apparently a mail daemon waiting for connection requests, and some other things,
What is
right?
daemon?
Daemon is a server, basically.
Okay.
And it's technically daemon, but everyone calls it a daemon. So down here, there's something listening on port 22, and that connection has been established. That's my session. Okay, that's my SSH session that's running right now that has me connected to the server. And if somebody else logs in, they'll show up under here also as another pair of processes on port 22. And I tried this earlier and it didn't work. So this thing right here on port 1209, that's the assess server. So when ODPs are live, and you can say assess blah blah blah, what it's doing is it's talking to a process that's listening on port 1209. So that's using client server model. And if we kill it off, then that goes away.
So can only one person assess at a given time then?
No. Only one person could connect to it at a given time, but as soon as someone tries to make a connection, it creates a new thread, and that thread does the communication. And the same thing happens with SSHD and HTTPD and all these other daemons. When you make a PuTTY connection to the secure server daemon, SSHD, you don't actually talk to that process. That process creates a new process, and that new process talks to you. So if we look at SSHD, right, so those are my two processes that are managing this current communication. This is the actual daemon, right? So this is the only one that's listening to that port 22, and it creates a new socket and sets up communication with myself or Andrew or Pavel or whoever. So this is something that you can take into account in PA5 when we get there shortly. Okay, so you got the basic idea, client server. So let's look at PA5.
Hopefully he's not having the tic-tac-toe game via server.
I think our book does that actually.
Oh, really?
I think there's a chapter in the book where they talk about client server and they use tic-tac-toe as an example. So PA5, you're making a chat program, okay? So it's going to be both a client and a server, so two programs. And the basic setup is you have a server sitting out there waiting for clients to connect. Client comes along and says, I want to talk to the server. So you run the client code, right? Tell it the address of the server, which will usually be your local host. And that establishes a two-way communication. So now whoever's running the client code can type, hit enter, and the server code prints out what the client typed. The client can type something more, hit enter, server prints it out. At the same time, whoever's sitting in front of the server code can be typing and hitting enter, and the client will display that. So it's a two-way chat program. Okay, pretty straightforward in its behavior. So basic behavior, each program waits for the user to type input, hit the enter key, transmits that entry to the other program via the socket connection, and at the same time, whenever input arrives from the socket, it should display it. It should not wait for the user to type enter to display what somebody sent to you. As soon as somebody sends you something and they hit enter, it should appear on your screen immediately. Okay, the server never exits, the client can exit. So you can Control-C your client code, or you can use an exit command, and at that point the connection should be shut down gracefully, and now the server should go back to waiting for a new connection request.
We have multiple clients connected to the server.
You may. You're not required to, but it's a good embellishment.
Is this a swing thing? Or?
So you can do it on the command line, you can do it on swing. Okay, complete freedom of artistic expression here. So at the minimum, you want to be able to do two-way communication. And here's a first attempt at doing this. So the server, wait for a connection. So that's running, it's waiting for somebody to connect. The client connects to the server. And now, client read standard in, send to server. And at the same time, the server reads from the client and prints to standard out. Now, we can put a loop here, and we've got half our program done. Because now the client types some stuff, hit enter, types some stuff, hit enter, types some stuff, hit enter. And while you're doing that, each time you hit enter, the server comes back from its read from the client, prints it, what it read to standard out, goes back, waits for some more. So now the client's typing stuff and hitting enter, and the server is displaying what the client is typing. Okay, but we also want the person sitting over here to be able to type and hit enter and have that show up on the client side. And currently this won't do this because we're not reading from standard in and sending to the client. So we might want something like read from standard in and send to client. And over here, read from server and send to print to standard out. And put that in a loop.
Are these threads then?
Yes, because this will not work correctly. So what's wrong with this?
You'll never get past the first while loop on the server side, essentially, without another thread, right?
Well, it will. I mean, it'll read what the client sends, print that out. It'll wait for the server to type something in, hit enter, send it to the client, and then it'll go back and read from the client again. But this is forcing your communication to go, I send a message, you send a message, I send a message, you send a message. Right? And if you're sitting down here, you've typed something in, you've sent it to the server, you're not going to come back to this step 3 until you read something from the server. So you're typing in a bunch of messages, blah, 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 and nothing's getting sent because you're waiting for the server to send something. And we don't want that. So what you want to do is split this into 2 processes on each side. So 2 threads. One thread that's responsible for reading from the keyboard and sending to the remote side. Another thread that reads from the remote side and prints to standard out. And if those are 2 separate threads, they're both happening at the same time. I can be in the middle of typing something in, a message comes in from the server, it prints it out right away. So they can take War and Peace and they can just spam that to me. And I'm trying to type and War and Peace is coming out on my display. That's what you want. Okay. Now if you do this in a GUI, right, you can have a separate window for input and output. So you're typing in your input and your output window, you're seeing War and Peace scroll by, and that's not bothering you because you've got your, right? If you do this from the command line, then everything gets jumbled all together, and that's fine. That's the intended behavior if you're working with a single window, which is basically what the command line is. But if you want to embellish it, you can go ahead and put some GUIs on top of this and go to town with that. If you want to do this from the command line, right, you don't need Eclipse for this. You can do this all just from VI, Javac, and Java. And there aren't that many classes we need to worry about, so it's not bad to put the code together yourself. And it's up to you how elaborate you want to be with this. All right, so other details. For this assignment, you get to work in groups if you want. Okay, so groups of up to 3 people. And if you're working in a group, don't split it up and say, you do the client, I'll do the server. Okay? Make sure that you understand all the different pieces of it, because this will be on the exam. the client server stuff. So you want to make sure that everybody in the group understands all the pieces. But it's a reasonable way to split up the work. Okay, I'm going to concentrate on the client side, you can concentrate on the server side, and you can concentrate on how we're going to shut down the connection or whatever. So ways to subdivide it. So you can do alone, groups of 2, groups of 3. And you're going to demonstrate this in class. Okay, so the other detail is this is due on Monday, a week from this coming Monday. Right, because 2 weeks from tomorrow is the last day of the quarter. And then there's no time to get feedback on this. So this is due earlier than 2 weeks. Okay, and then starting that Monday, we'll demonstrate in class. So demonstration is really just sort of coming up and showing us what your code does, and it can be a couple of minutes. It can be longer if you've got more bells and whistles. All right, when you run the client code, you want to tell it where the server is located. And typically, the server is going to be running on the same machine as the client. And when you make a connection to the client, and we'll talk about how to do this after the break, you have to tell it the address, right, the IP address. IP address 127.0.0.1, that's reserved. That always means your local machine. So if you're running on the same machine as the server, you can say connect to 127.0.0.1 or the name localhost, and that always resolves to that IP address. But if you run your server on a machine over there and you know its IP address, you can run your exact same client code, but instead of localhost, give it the IP address or the name of that machine, and it should connect to that server. And once you get this working on one machine, it works across the network automatically, right? Which is part of the fun of this, because now you can, go across town and chat with someone. Okay, is this making sense? All right, the other detail to think about is how you're going to shut down the connection. So if you're sitting in this loop and the client hits Control-C, right, or Control-D or whatever to exit their program, and this thing is waiting to read from the client, hopefully it's going to do something reasonable, right? Bad responses would be to sit here and wait forever for a client who no longer exists. Well, that's not good. Worse would be to try to read from the client and throw an exception because the client doesn't exist, and then your server exits. That gets a frowny face. Or you try to send to the client and the client doesn't exist and it throws an exception. So you want to think about how you can gracefully shut things down so that when the client exits, the server goes back here to where it's waiting for a connection and then goes back into this. And one way to control that is, instead of Control-C over here, send an exit command, right? So like !exit might mean I want to get out of here. Or somehow detect end of file. But you should also think about how you can handle if the person just abruptly Control-Cs or their system crashes, right? And can you handle that on the server side?
So only use try catches in this.
Yeah, right, exactly.
If it catches it just exits.
Yeah. All right, so let's take a quick break, and then let's start looking at Java implementations of this client-server model. And it's really straightforward doing the stuff in Java. Okay, it's 2 classes basically we're going to have to deal with, and the 2 classes are effectively the same as each other. So we're pretty much done.